So we're going to be reviewing AP Physics 1 course review today. We've got the AP exam. I will be going over the topics that are in the course briefly, enough to review concepts and equations that are necessary. All right. So, I believe the first you probably learned kinematics, right? Kinematics. And kinematics is broken into two sections: one-dimensional motion or two-dimensional motion. One-dimensional motion means you're moving in one of two ways, just forward or back, right? Where 2D motion, and so there's only really one axis that you use to plot the position of something moving on in one dimension. While if you have something moving in two dimensions, like if this was a room and we were looking down from the ceiling, you consider these two separate axes, y-axis and x-axis. Some walk along any certain path, and you would be able to track this person as they go along that path by finding a coordinate the way you've been doing it for a long time, x, y, right?
Yeah.
Okay. So once you decide that you're going to track something's position in one dimension, you would recognize that there are two kinds of motions that you might actually observe while watching an object move in one dimension. And so you will either see constant velocity motion, or you'll see accelerated motion. And accelerated motion can be either speeding up, which would be commonly called accelerating, but it also includes slowing down, which would be called decelerating. Oops, sorry. Okay. And so let's take the first case, which is you're watching something that's moving at a constant velocity. If you're watching that car, for example, drive along the road at a constant velocity, you see that it's moving equal distances each time. So if this is where it was at some time value t1, this is where the car would be at t2, t3, t4, and so forth. And the fingerprint of constant velocity motion is that these time distances for each of the times in between t1 and t2, or in between t2 and t3, and so forth, those are all equal, right?
Yeah.
When you create a plot of position versus time, if you decided to call the motion that this car is driving along the x-axis, then you would, of course, naturally need to put some values here, 1, 2, 3, 4, and so forth. And if each of these were, let's say, 5 feet, then after 1 second, it went 5 feet. After 2 seconds, it would be at the 10-foot mark, and so forth. And you would end up realizing that this graph is linear, right?
Yeah.
What does the slope of this represent? the slope of a position versus time graph represents velocity. So if you took any 2 points, let's say we took the 0, 0 and the 1, 5 point, and we looked at this piece triangle like you would in a math class. So we have this point and this point. We call this delta x, how far its position changed, and this would be delta t, how much time related to that displacement. And in math class, learn slope as rise over run. You would do a delta x over delta t, and that unit would be in meters, since x is measured in meters and time is measured in seconds. You'd realize that the slope, the units for the slope are meters per second, which indicate to people, if they were unsure, oh, that's velocity, right? One really important idea: velocity is always delta x over delta t, where delta x is a displacement and delta t is the time interval required displacement. And we already said in my picture up here that for 1 second, if each of these were, 1 second, and t2 was 2 seconds and t3 was 3 seconds, then it's pretty straightforward to see that the picture is moving 5 feet per 1 second, right?
Yeah.
Move 5 feet, then another 5 feet, and it makes sense when you look at the graph. Okay, each second it's showing that the position is changing by 5 feet, so therefore the slope is 5 feet per second. Any questions about that? Okay. I'm going to erase this. The other kind of graph, well, before I even say that, about the kind of graph, when you have a position versus time graph, there's no key that it has to be sloping upward. This graph could certainly go into this bottom quadrant, which is the negative quadrant. Somebody that's moving along this axis, but they're in the negative region of that axis. So if you were and so if this person had started where he is starting in this picture, is if this was at t equals 0 seconds, then the y-intercept would be 1 because he's starting there, right? So this right here represents x initial, or some class. And if he was moving to the right, that would still continue sloping upward because his position is going from 1 to 2 to 3 to 4, and the sloping graph would indicate the values 3 to 2 to 3 to 4. But what if he was on the other? So let me jot that in here. He's moving upward. And what is this slope? This is a positive slope here. And since the slope is a positive slope, means that's a positive velocity, and positive velocity means he's moving to the right.
Yeah.
Velocity is to the right. On the other hand, if he's moving to the left, that would be considered a negative velocity, and the slope of the graph, since the slope is would have to be negative, like this, right? As he starts at the 1 meter mark and then he starts to head left, it won't be too long before he's at the origin, which would be when he's right here, and his position is 0, this point right here, at x equals 0. And then moments later, he'll be at the 2 point, and then at the -2 point. And those correspond to these points down here, right? -1, and this one would be a position of -2. And so the sloping to downward, the negative slope, would just indicate leftward motion. And in fact, the slope is constant, indicates the velocity is constant, because slope is the distance you cover per second, right? Okay. So now I feel I can move on to the next. If something is moving along at a speed again, as we said, and it happened to be the simplest case, it's a nice upward diagonal line, again, velocity, what formula would we use to determine how far he's traveled in a certain amount of time? That would be d equals vt, or you might call it x equals t. And that's actually a model of the graph. The mathematical model for constant speed motion is just linear. It's y equals mx plus b. If the y-intercept is 0 here because he starts right at the origin, b gets canceled and is just called 0. On your y-axis, you have a position variable that we call x. The slope, as we previously is called v. And on the x-axis, we have t, right?
Yeah.
So x equals the formula you would use for any constant velocity motion. If somebody's asking you to solve for distance, they'd have to give you the velocity and the time, or they could ask you to solve for velocity, and they'd give you the distance and the time, or they could ask you to solve for time, and they'd have to give you the position or the distance and the velocity. But they can give you any two things, and then you'd solve for the third, right?
Yeah.
Okay. If somebody is moving at a constant velocity, what will the velocity versus time graph look like? It will be a flat line, right? If that person in my picture that I drew was walking at 5 meters per second, like I had said, then at all time values, his value for his velocity is that value. So that's called a constant velocity, right?
Yeah.
What does the slope of this graph represent? Slope versus t is acceleration. Yep. Because what is the slope of this? It's 0, right?
Yeah.
So if the slope is 0, that means there's no acceleration. That means his velocity is not changing, which is true because he's walking at a constant speed, right?
Yeah.
Doesn't have to be that way. Of course, somebody could be accelerating. We'll look at now. That gets us to the next kind of motion in my little chart over there. We're now moving from constant velocity motion to accelerated motion. So for accelerated motion, if you're watching a car that's fixing, it will travel some distance in the second, but then it will travel larger and larger distance each second because it's speeding up. T1, T2, T3, T4. And if you compare the distances that it's traveled each second, you see that they're increasing. They're increasing incremental distances since velocity is increasing. And since velocity is how much distance you cover per second, if your velocity is increasing, it means the distance you cover per second must be going up, which in this, what's called a motion map, would indicate the picture of the car or the picture of the person, whatever it is that's moving, are at further and further distances after each, or there are greater and greater displacements per second. Okay, so if you decided that you wanted to graph that, we'll start with the most obvious case, which would be a position versus time graph. If you've got a position versus time graph for something that's accelerating, it won't be linear anymore. You can still measure its position at nice equal time values, which would make sense at 1 second, 2 seconds, 3 seconds, and 4 seconds, let's say. And let's just say it started at 0, 0, started at the origin at 0 seconds. And let's just say 1 second later, he's also at the 5 meter mark. At 2 seconds into accelerating, he won't be at the 10 meter mark because he's going to cover an extra distance in that second, a distance greater than 5 meters. So it won't be going from 5 to 10. It might go from 5 to, let's say, 12. So if this was the 10 and this was the 15 mark, for our 2 second mark, we wouldn't want to place it right at 10 because that's constant speed. We'd have to lift it up a little bit and maybe put it up here. And then when we go to the 3 second mark, he won't be at the 15. It won't go 5, 10, 15 like before because, again, that's constant speed. He'll be a little further than the 15 mark. Maybe that's, who knows, maybe at the 20 mark. And when we did that graph, here, the linear one would have looked more like this. And that gentle curve, the curve indicates that object accelerating. Right? Jeremiah, you're still there, right? I want to check in and make sure you're still there. So a linear position versus time graph is velocity. When it's curved position graph, it's called constant acceleration. And I'll talk about exactly what that means in just a moment. But just know curved graphs mean you're accelerating. Speeding up, faster and faster, covering larger and larger distances each second. The next natural thing to do is say, okay, well, is there an equation that models that graph? I'll try to do a little nicer job this time with my graph that I drew. So let's say your position versus graph now is curved. It turns out that since it's curved, it has to be a power of 2 for t. X equals vt is raised to 1. That's the hallmark of linear. Anything that's linear is the first power. Something to be curved, this t exponent has to be 2, has to be squared, because any squared graph is curved. So turns out that the formula for is 1/2 at squared. That's a term that we use a lot over the course of the year. Right? And that x could really be considered a delta x. And the delta x really would be displacement after t seconds has elapsed. The reason we called it a constant acceleration is because acceleration is defined as how much your velocity changes per second. So if I go back to our old graph that we looked on the right, e versus t, if something's accelerating at a constant rate, then the speed or velocity is increasing the same amount per second. So if this was the 10 meter per second mark, and this was 1, that means it gained 10 meters per second in the first second. What its velocity is after 2 seconds of acceleration, you'd see that it's now meters per second. And then if you check velocity at 3 seconds, you'd see that it's moving at 30 meters per second. And so when you do a slope calculation, just like we had before, you'd say, okay, we've got 2 points that we've arbitrarily chosen on this graph. It makes a triangle. We call this bit delta V, the change in velocity, and this bit here, the time. And when we do slope, as we always do, it's a rise over a run. When you do delta V over delta T, that is the definition of acceleration. And so constant acceleration means if you looked at 1 second of motion in my graph, the delta V is 10 meters per second. It doesn't matter whether you look in between 0 and 1 seconds, you'd find the change in velocity was 10. If you looked in between 1 and 2 seconds, you'd see the change in velocity is 10. If you looked in between 2 and 3 seconds, you'd still see the change in velocity was 10 meters per second. That's the idea of what we call constant acceleration. Your speed is increasing by the same amount each second, which is why the velocity versus time grows. Right?
Yeah.
Okay. So A in this formula, delta x equals 1/2 AT squared, is considered to be constant. It's normally given in a lot of problems. If it was a free-for-all problem, what value would we put in for A? If you were dropping a penny, the acceleration would be g. And this is a very important formula, in my opinion, because it turns up a lot on a lot of the multiple choice questions during free response. It's very common that this turns up and you have to reference it. So I consider this to remember. Delta is just a displacement, is equivalent to 1/2 AT squared. So practically, if A was as a number, and they said how far has it traveled, you'd put in the value for A, you put in 3 and square it, and you would calculate out whatever that displacement was for a second interval. Does that make sense? Okay. Thing is, so that'll again, this equation, delta x equals 1/2 AT squared, is the model for this. The next thing is, what is the model for velocity versus time graph? Because if you're accelerating at a constant rate, your speed increases the same amount each second, as shown on this velocity versus time graph right here. So if we want a model for that, well, it's linear, y equals mx plus b. On our y-axis is velocity. We're trying to figure out, can we find out a formula that gives us velocity as a function of time? The slope of this graph is the acceleration, as we previously figured out right here. The slope is acceleration. On our x-axis, as usual, is time. And in this case, the y-intercept is the initial velocity. So this formula is normally written v initial plus at. And a lot of times it's written v final, then v as a function of t. But those mean the same thing. And that's one of your kinematic equations.
Yeah.
So in this picture that I've drawn, the y-intercept was 0, indicating this object started at rest and began to accelerate, which is why b is 0, and you'd just be left with v final equals a times t. So for problems that commonly turn up an object is dropped, initial velocity is 0, right? When you drop anything, it starts out with no velocity, and therefore the final velocity at any given time is just a times t.
Okay.
Does that make sense?
Yeah.
Most cases, that's what they give. Could they, in theory, say someone decides to throw a basketball downward with an initial velocity of negative 20 meters per second? Yeah, they could. It's not common, but if that were the case, the model would be v final equals negative 20, and then you'd have minus 9.8 for g times t. And if they said, how fast is that basketball moving 5 seconds later, assuming he throws it downward with a speed of throws it downward with a velocity of 20 meters per second, this formula will do that. It's taking into consideration that it started with initial downward velocity, that's why it's negative 20, 20 meters per second, and then the negative 9 times t, how much speed how much the velocity increases while falling for a certain amount of seconds t. Okay? All right. So there's one more kinematic equation, and then we'll have more or less reviewed. Well, there are a couple other things, but we can comment on them quickly. If you had a velocity versus time graph that looked like, say, this and this, if they asked what is the displacement, let's say it went up to the 5-second mark, and these were different tick marks here. Say it was, I don't know, like this, and I didn't do a good job at that, but it doesn't matter. The point is, the displacement is the area under curve. Did you learn that in your class? Or under function? Under, what I mean by that is, if the velocity increased linearly for some amount of time, and then it plateaus off, indicating now the object's moving at a constant velocity, and then they say, let's stop motion at 5 seconds. How far did the object move? Or another way to word that is, what was the displacement during that 5 seconds? It turns out that this area here, this triangle, this has a certain area, and then this square here has a certain area. And so the area is the displacement. You could literally make a free problem and say, oh, okay, if I can figure out the area triangle, then I'll have the displacement during the first couple of seconds graph. That would be called D1. And then if I can figure out the area of this giant rectangle, that would be the displacement that occurs during constant velocity motion. And if they want to know the total displacement of my areas, does that make sense? So, and that turns up on a couple different topics in physics, and a lot actually as you go through college, but in introductory physics at your level, it turns up a few times. And so my point is, they would have to give you some values. If they showed you on the graph that this was the number 5, and then it plateaus off, and they said that this was the number 1, then when you're trying to work out the area of this triangle, you'd say, okay, here's a triangle. The width of it is 1, right? Because they're saying that this part is 0 and this part is 1. Does that make sense? And then the height of the triangle would be 5, because it's saying that this goes from 0 to 5. And so you'd say, oh, okay, it's 1/2 times 1/2 times the base times the height, right? Because the base times the height would give you the area of the rectangle, but you're just going to half of it. So this would be an area of 2.5. If it was right, if it was full, you'd say its area is 5. It's half of that, so the area is 2.5 meters. And you would do the same thing for the rectangle, then add them together to get the total displacement during that 5 seconds. Okay?
Yeah.
All right. I'm going to just list. Well, I'm going to go over the last kinematic equation, and then I'll list them for you, and then we'll move on. So the most common one you use equals 1/2 AT squared, or you could call it x equals 1/2 AT squared. That means the same thing. You could have V final equal initial plus AT. That tells you how fast something's moving in direction as well as speed some amount of seconds after acceleration begins. The very last one is V final squared equals initial squared plus 2A delta x. Remember that one?
Yeah.
So that one is the only one that doesn't have time, and that turns up to be very useful. So whenever you read a problem and you have something to do with kinematics, the first thing you should ask yourself is, was time mentioned at all? Did they give me time, or did they ask me to solve for time? And if they did not, then that indicates this is the formula that you would need to use to solve that problem, because there's time in it. Right?
Yeah.
Where delta x is still the displacement, A is acceleration, V initial is the initial velocity, and V final is whatever you're solving for. often that's the case. They'll say, what is the final velocity after place meters if the acceleration was per second squared? And you just stick the numbers in. All right, that's the quickest review I can do of kinematics, because kinematics is a pretty full topic. Teachers often a while to get. But any questions? Yeah.
No.
On try to go through this quickly to vectors.
Okay.
So if you have a vector, let's call it a force vector, then you need an angle and a length to describe that vector. Specifically, when I said you need a direction. So vectors need, or they don't need, they have direction and magnitude. Because magnitude is the length, right? And they also can have components. So this would be considered the F component because it's parallel to the x-axis. This would be the y component because it's parallel to the y-axis. And had they put the magnitude of this force vector as, let's say, 50 newtons, that means the physical length from here to here is 50. And they might even say, okay, the direction of this force is 20 degrees. Well, that means you could work out the components by just doing some trigonometry and saying, okay, this is going to be representative of 50, this is going to be 20 degrees, and therefore this one will be cosine 20, because adjacent always goes with cosine, and this one will be sine 20, because sine always goes with the one that's opposite. And so in general, the x component is the magnitude of the force times cosine theta, and y component is the magnitude of 4 times sine theta. Yeah? Right? Okay. Can those be plus minus? Yes, they could. If the force was going this way, then this component would be negative. This can be positive. So you can have negative components. But the magnitude is the absolute value symbol, as can be shown here. So it's always positive. Okay? Then you can add vectors. I'm not going to by any means do a whole example of adding vectors. It'll take too long to try to review the whole course, but I can quickly describe the idea of adding vector addition. It's called head-to-tail for vector addition that I most commonly use as opposed to a parallelogram method. I think is as intuitive. I feel like the head-to-tail method makes sense. Oops. Head-to-tail addition. So if they happen to give you two vectors that have to be added, which I think is a very likelihood of literally having to make a full computation for vector addition, but there are some things like Coulomb's law where you might have to mentally think about vector addition. An example of that. But let's just say there was some vector A, and we had another vector like this, vector B. If we want to add them head to tail, you would literally take the two vectors and stick them together. This is known as the head of the vector. And since this is the tail of vector B, the head and the tail have to be stuck together, hence the name head-to-tail method for vector addition. And I would literally go like this to it. This is now vector B, and this was vector A. And what's known as the resultant goes from the tail of vector A all the way to the head of vector B. That's called the resultant. And there's a fairly involved trigonometry process for working that out, which I'm not going to go over. But very, very quickly, the idea would be you'd have to work out what the x component is for A. If this was A, you'd have to work out, if this was vector B, you'd have to work out what the B component is for vector B. And these would have to get added together, right? And so the resultant, called vector C, has an x component Cx, which is right here, all the way to there, which is equal to the sum of AX plus BX. It's however long AX is right here, plus however long BX is right there. And similarly, the resultant has a y component called CY, which would be the sum of AY plus BY, right?
Yeah.
AY plus BY. Okay, that's the general idea. Ultimate goal generally is to figure out what is the physical length of the resultant vector. That's normally the answer. And if you can go through that process I just showed, work out what CX is, and you go through that process to work out what CY is, then you would use the Pythagorean theorem to work out the physical magnitude of the and then if you needed to figure out the angle here, the direction of vector C, it would be the inverse tan of CY over CX, because it's opposite, and CY is opposite to that angle. All right.
Okay.
That's a very brief view of vector addition. Oops. A common occurrence of using that might be Coulomb's law, where they say this is a charge. All these charges placed on paper equal charges, and they would ask, in which direction will this charge move? If this was considered charge 1, this was considered charge 2, this is charge 3, and this is charge 4, they'd say that charge 1, 2, and 3 can't move. They're locked down by being glued to the table, and then you drop charge 4 in that spot. You release him. Which way does he go? Well, this is like a mental application of using vector addition. You'd say, well, this chart, well, and if you're drawing a free body diagram for charge 4, you'd say, well, he's going to be repelled from charge 1, F1, because charge 1 here is pushing him to the right because they repel.
Yeah.
Which way will he go because of charge 2? Well, charge 2 is also going to push him, but the magnitude wouldn't be quite as long because this one is further away. Right? That hypotenuse is longer between them than the distance between 1 and 4. And then you say, well, which way will he go due to charge 3? Well, charge push him. He's going to push him upward, right? So this will go up, and you'd say that's, I didn't mean to have that 4 there to confuse things. That's the force from charge 3. So if they're asking in which direction will this charge actually go, this would be a vector addition problem. You'd say, well, vector 3 would be equally as long as vector 1. This is, I guess, what I was calling F3 and F2. I'm just going to call them 3, 1, and 2. And so vector 3 and vector 1 would be equal because they're all equal charges, and they're all, the distance from 1 to 4 is the same as the distance from 3 to 4. And Coulomb's law says the electric force is equal to K Q1 times Q2 over R squared, right? And so since the distance is greater for 2 and 4, that's going to be less of a force. That's why this vector here was a little shorter. But since these are the same length, they have same distances and same charges, you add head to tail, you shift one up and up there and add head to tail. The result of just adding 1 and 3 together puts a force in this direction, right?
Yeah.
But then you say, well, what is charge 2 over here doing? Well, he's also pushing, as you can see here, as I'm coloring that in, also in that direction. So which way will he go? He'll have some force right here from those first 2 charges, plus a little bit more force from the charge 2 that's in the bottom left corner. So the overall direction would be up and to the right. Does that make sense?
Yeah.
So that's like you do that kind of mentally for their multiple choice questions. You're not sitting there working out exact trig, values and sines and cosines. You're just thinking of the concepts of vector addition and how they apply to that. Okay, so now we're moving on. Let me look at, because I have a book here in front of me. Projectile motion turns up a little bit. The only one I'm going to really talk about in detail would be the one that I see turn up the most commonly. Projectile motion is 2-dimensional motion. Because as something, the common problem is they show some sort of table and they'll show a ball rolling off the table. And so it has some horizontal motion as it goes through the air, but it also has some vertical motion down as it continues to drop. That's the reason it's 2D motion. The one key thing you have to remember that turns up on the AP exam a lot is they reference how long it takes to fall. And the ball, if you drop the ball straight down, it would be in the air for the same amount of time as one that rolls off the table. And you could use that formula that we mentioned before to determine the time that it takes to fall straight down for a ball that's dropped would be 2h over g square rooted. And so even if the ball, if they're asking how long does it take the ball to go from the edge of the table to the floor, it's the same amount of time as the one that you dropped, 2h over g. And if they're asking for what's called the range, which goes from here to here, it moves horizontally at equal intervals. So if it moved that far in the first second, it would move that far in the next second, that far in the next second. And so every second it moves horizontally equal distances because the horizontal velocity is constant. And so since our formula for constant velocity motion was x equals vt, you could chart out this thing's horizontal position by just plugging this formula in for t here. That problem happens to turn up pretty frequently. And this v is the initial velocity in the x direction that it has right when it comes off of the edge of the table. And x would be some horizontal position like this value x or this value x. It'll get larger and larger as it goes through the air. I'm sorry, I didn't mean to say, what I'm saying is true, but that's if you're using x equals vt. So as time continues getting larger, the position x gets larger and larger. If they ask you for the total range, like I had said before, the total range is this formula right here. Also vertically, it doesn't fall equal distances each second. In the first second, if it fell that distance, in the next second it falls a larger distance, and in the third second it would fall a larger distance because the acceleration is happening only along the vertical axis, which is straight down. Right?
Yeah.
Okay. Moving on. The next would be circular motion. No, sorry. The next would be just Newton's laws, which we'll do quickly. Newton's laws, the most common one is his second law. That's stating that the acceleration of an object, how rapidly it speeds up, is proportional to the net force and inversely proportional to the mass of the object. So A is proportional to F net, and A is inversely proportional to M. So if you push harder, it speeds up more. If you continue to be given heavier and heavier objects to push, and you always push with the same force, the increased mass of all those heavier objects would mean that they'll all slow down more, speed up slowly, since there's an inverse relationship between A and M, right?
Mm-hmm.
Also, the concept of F net is that you have to add forces up. So if there's somebody pushing over here, F1, and somebody also pushing F2, then the net force would be F1 plus F2. In general, F net is the sum. Let me do an extra squiggly. It's the sum of all of the forces, and this would be along the x-axis, this idea that I'm showing here. And if he was pushing to the right, it would be a positive value, and this would be a positive value, and you would just add them up. If it was 2 newtons of force and somebody else was pushing with 5, then the net force in the x direction would be 2 plus 5, you'd say 7 newtons. On the other hand, if somebody is pushing to the left, that force would have to be distinguished from rightward forces by giving it a negative sign. So this would be like negative 3 newtons. This would be plus 5 newtons. And so if we're doing the net force would be 5 minus 3, which is just 2 newtons. That's the amount of unbalanced force to the right, because 5 newtons is stronger than 3 newtons, so there's a leftover unbalanced amount of 2 newtons to the right. And if you were asked to solve for the acceleration, that's the net force value that would go in for F net. You'd have to divide by the mass, and that would determine what the acceleration rate is for the object. Good? Okay. This is also a huge unit, so I mean, I could spend 10 hours trying to review this unit, and obviously I won't and can't, but there's a lot of specific problems that are common. I'll try to go over the ones that I know are most common. If something is hanging from the ceiling, the downward force is mg, and the tension would have to also be mg, because these are in equilibrium. So what's called equilibrium indicates the net force is 0. Oops. Indicates net force equals 0. So F net physically equals 0. So that's why these would have to be equal. This one would be downwards, which would be negative. This one would be plus, and those add up to provide 0 net force, and so it shouldn't move. If something is on a ramp, those turn up a lot on AP Physics problems. They show a ramp of some sort. They show the angle like this. If there was no friction, which is common sometimes for multiple choice questions, but sometimes they throw friction in there. There's no friction and no air resistance, and this block was stuck up here, it would still accelerate in the downward direction. And that's because the weight of the object downward, which is normally just mg, ends up having a component direction of down the hill, down the ramp. It's this piece right here. Turns out that these angles are equal, and since this is opposite to that angle, the part that you're often interested in is the x component of gravity, which would be mg sine theta. So that means if you were asked to draw a free body diagram for that block, it feels a force due to its own weight, gravity, mg sine theta, that's going to accelerate it down the ramp. It would still feel a normal force straight up, not straight up, but up and away from the ramp, perpendicular to the ramp. And, also still have, you would show, well, I'm not really doing if someone said just draw a free body diagram, all you'd really show would be Fn, the normal force, and Fg. Turns out that Fg can be broken down into the components. So if you were asked to solve for something and you had to work out what that x component force was, it ends up being mg sine theta. But on free... Yeah, sure. We're just pausing this for just a moment. He said he's coming back. Yes?
Can I pause for one thing? I think I gotta go take care of something for my mom.
Okay.
You can just stay on the line. I'll be back. Give me like just 5 minutes.
Okay. All right, so I'm going to break this into 2 different parts. The person I'm tutoring said something that he has to go do for 5 minutes. That was an emergency. So I'm going to go ahead and stop this recording, and unless I can pause it. Let's see. So we're pausing. I'll break this up. It's almost 1 hour in anyways, so we'll just call this part 1. And I will post another one and call it part 2.